So let's talk about this idea right here. We first need to introduce a definite integral. Okay. What is a definite integral? Let's go back and do a quick review, though. Quick review of an indefinite. This is from 4.1. A quick review of an indefinite integral. This is something you would have seen back in 4.1. Find the general solution. Dy dx equals 3x squared minus 1. Is this ringing a bell?
Yes.
This was back in 4.1. Before things got weird in 4.2.
Yeah.
We moved the dx over, right? So dy was equal to 3x squared minus 1, all multiplied by dx. Keep it coming.
Then we add 1 to the exponent divided by the exponent.
There you go. So that's called taking an integral. Remember this symbol?
Yes.
Okay. If you take the integral of dy, that's just y. If you're taking the integral of the sum or difference of multiple terms, that's just like taking the integral separately. So it's integral of 3x squared dx minus the integral of 1 dx. You following still? So it sounds like some of you guys have the right idea. When you're taking the integral of something with a power, come on, keep it coming. You increase or decrease? You increase the exponent by 1, and then you divide by it, right? So this is going to be 3 times x to the third over 3 minus.
Which dx just turns into x.
The integral and dx are like inverse operations. It's kind of like dividing and multiplying. The integral and the dx cancel each other out. Because dx is like a derivative and the integral is the opposite of that. So where are we? So we get this one. What about this one? And then the 3's are gone. So y was equal to x to the third minus x. Ooh, we're getting something.
Plus c.
Plus c. Okay. This is what's known as the indefinite integral. Really what it helps find is the antiderivative. We good on that? That's the indefinite integral. It helps find an antiderivative. Well, here's a definite integral. Okay. So this little definition we had from 4.2 You remember this goofy little thing that you all have not grown to appreciate yet?
We have not.
It's equal to this. An integral from a to b of f of x dx. Now, I know we haven't done a ton of it, but taking an integral, are we getting a little more, just like what we just did. We took an integral, right?
Yeah.
That's most of what a definite integral is you take an integral. But the difference is we have a lower bound and an upper bound. Okay. So this is called the definite integral from A to B. A is the lower limit, B is the upper limit. Kind of like that number 61 we were just working on. We were trying to find the area between 1 and 3, so 1 would be the lower limit and 3 would be the upper limit. Okay. So just a couple of special, these are just best to memorize. Special definite integrals. These are actually pretty self-explanatory, but well, at least the first one is. I guess they're self-explanatory if you think about it this way. That number 61 that we spent forever on, what is it we were trying to find? Area under a curve, right? Between 1 and 3. What if the upper bound and the lower bound were the same number? What would the area under the curve be if we're going from 1 to 1? You understand what I'm asking? So, what if we're trying to find So we're trying to find the area under a curve, but it's from one number to itself. Is there going to be any area? No. So this would equal 0. If you're trying to find a definite integral, but the upper and lower bound are the same number, the integral is 0. Just best to memorize that. Pretty self-explanatory. Okay. If f is integrable on AB, then the integral from B to A of f of x dx So if you switch the bounds of integration, essentially this is what it's saying. If you switch the bounds of integration from B to A, and then here it's from A to B, if you switch the bounds, you just get the opposite of what you started with. Okay.
So it would be negative area?
Yeah, well, it would be area underneath the x-axis rather than above it. That's what the negative sign means. And a few more properties. These are pretty similar to the derivative properties. If you're taking the integral from a to b of k times f of x d of x, or dx, where k is a constant, you guys could probably tell me what's going to happen here. K is a constant. What do we usually do with them? We take them out? We most often have done with constants. I guess if the constant's multiplying the function, you just pull it out. So this equals k times the integral from a to b of f of x dx. Okay. Second one, if you're taking the integral from a to b of the sum or difference of two functions. And you guys could probably tell me what's going to happen here.
Can you send Maddie louder to the front office, please?
Yes. Ooh, you're in trouble. Listen, I think I heard somebody say it. What do you think is going to happen here?
Taking the integration.
Just separate it. It's the integral from a to b of f of x dx plus or minus the integral from a to b of g of x dx. Okay. This was the part I was talking about that comes from 4.3. This is really all you needed to know from 4.3. It introduces what a definite integral is. It has you kind of mess around with a few things. It wasn't really important enough to make a day out of it. So we're moving on to 4.4 now. Okay. Fundamental.
Oh my gosh!
Theorem.
There it is. It's
of calculus.
Poor Maggie to read. Yeah, she's not going to hear the fundamental theorem of calculus. Come back. That sucks. It's around the whole year just for this.
Yeah. If we call up Kate on the phone, get him on speakerphone so we can hear this.
Nah, it's his birthday.
It's his birthday today?
Actually, this is the best birthday present we could possibly give him. Let's phone him. Here, I'll phone him up. Phone him up. I got it.
Is continuous.
Tell him to tweet
On the closed interval
Going through my contacts.
A to B. Oh, by the way, to find the area under a curve between A and B, the function has to be continuous between A and B. Right? So that you can actually find an area under a continuous function. Anyway, that's what it says here. If f is continuous on the closed interval A, B, that means we can take the integral.
Really? Yeah.
And you guys tell me what this means.
Oh, shoot.
Capital F. You've seen that before. The reverse thing. Let's write that down. F is the reverse thing. No. F, yeah, is the antiderivative. Now just remind me, how do we find an antiderivative? By taking the integral. Yep. You find the antiderivative by taking the integral. It's the antiderivative of f, little f, on a b. Now here's the theorem. Wait for it.
Oh, here we go.
Pause for effect.
Leave a message.
Don't you hate that in like those reality shows where they're supposed to give an answer but they wait for some stupid reason?
Yeah.
Where they cut to commercials?
Dang it.
So we're actually going to leave it here and we'll talk about this. We'll talk about this next Tuesday. The integral from a to b of f of x dx is equal to. Well, you guys could probably figure out part of this.
Why? Because I'm actually.
What are we finding? Hey, come on.
Okay, sorry.
What are we finding when we're taking an integral? The antiderivative. What is the antiderivative of f of x? Big F. Okay, so write a capital F.
Oh my God. It's a capital F.
But we have bounds of integration. Okay?
Oh no.
There you go.
Oh no.
That's the fundamental theorem of calculus.
This tells me.
Tells you nothing, right?
Absolutely not. I think it tells the biggest double everything. Oh my goodness.
This is the area.
Boom.
Oh my gosh, we just did all that work.
Oh, that is so much easier.
Area under the curve.
No, I'm blessed. I feel very blessed on this day that it's a symbol.
Okay?
It's like the fundamental principle, or the fundamental theorem of calculus.
It's convenient.
It's like Orphan's wife is a
It's like the square root
Convenient
of pi
to write.
squared.
Write this down. It's convenient to write it this way, just for organizational purposes, especially for the boys in here who sometimes can't organize their papers and things like that.
Mr. Huff, I thought you were on the boys' team.
Yeah,
You guys
Mr. Huff.
cheated.
You won! No, how many times? No, we didn't. We went to work. We went to work. He drank like a gallon of water.
For what?
Because it was like,
Was that a fear factor type thing?
no, it was like who could gain the most weight by the end of the games got the points. He drank like a gallon of water and then dumped another gallon on his head. Aliens.
That's true.
She runs away from the guy bringing her here and gives him 10 points instead of 5. This guy runs out
So
with like 10
let's look at I can't remember what that equation was we did at the beginning of class. It was f of x equals 25 minus x squared between 1 and 4. Let's take a look at this problem again. We figured out a way to do it using infinite number of rectangles. That was sure fun.
Yeah, that was pretty fun. Thanks, Mr. Huff.
But let's find the area between 1 and 4 using the fundamental theorem of calculus. So we're going to go the integral from 1 to 4 of 25 minus x squared dx. So using some of those cool properties we talked about, if this is the sum or difference of multiple terms, so we can just do, we can separate the integrals.
Oh my goodness.
What's the integral of 25 dx? 25x, and the integral of x squared. X to the third over 3. So referencing what I wrote up here, this right here, isn't that capital F? So once you have the antiderivative, most textbooks and most calculus students, when they learn this, they would just put a vertical bar right here and put the bounds of integration from 1 to 4. Or it could be a little bracket, like, it doesn't matter. Okay. Subway. That's right. So, hey, you'll remember this, Courtney, the fundamental theorem of calculus. Anyway, what we now have to do is we have to figure out capital F of 4 minus capital F of 1. That's all we got to do now. So if you plug in a 4 into capital F, where this right here is capital F,
Okay.
it's going to be 25 times 4, which is 100 minus 4 cubed, which is 64 over 3. That's F. That's capital F of 4. Now we subtract capital F of 1. So 25 times 1 is 25 minus 1/3. Yeah. So add that all here.
Okay.
If you're doing your arithmetic correctly, what should we be getting?
54.
75 minus 63 thirds. But 63 thirds is just 21, and that equals? Look at that!
Oh, this is so cool. I love math.
So rather than having to do those summations with limits, we can do it this way.
Hey, can we do this on 4.2?
No.
Oh.
What's that?
I bet you just made this up first and then made up part of it. Just feel like this whole thing.
Yeah.
Like they made this way down, and they're like, how do you know that? And he's like, oh, it's just really long equation. They solved it, and then he just laughed at it. Like, I think we should.
So here's something to try on your own.
Yeah.
We're going to throw some trig in here.
Oh my. Okay, trig.
Well, we'll do an easier one here. Here's an example.
Everyone's something to just put trig in it. I got just way hard.
Try this one on your own.
Why is trig like Satan? Because it's not like numbers, it's these magical formulas.
Yeah.
No sense. It is like these weird rules just like the trig. They don't make sense.
Find the integral from 1 to 2 of x squared minus 3. Let's go. You guys do it.
Alrighty.
Integral from 1 to 2 of x squared minus 3 dx. Not next to this. And then when you're done with that one, try this one.
There's no fundamental theorem for that one.
Try this one here. Yeah.
It's a chapter one where you like average the rectangles on top.
Oh, I see what you're saying. That's probably what led somebody to think of it doing it that way. Probably.
Is this a negative number? Oh, there's another one.
Try that one once you finish with part A. Well, hold on. Let's finish. All right. What you guys get for the antiderivative here? Well, that's the answer, but the antiderivative to x squared minus 3. And then we evaluate that from. Okay. So the antiderivative of 2 minus the antiderivative of 1. 2 cubed?
8.
So it's 8 thirds minus 6, and over here, 1/3 minus 3.
6 can turn into 18/3.
6 can be 18/3.
3 can be 9/3.
So this is negative 10/3. And then that's 9/3. 1/3 minus 9/3 is negative 8/3, but really you're subtracting a negative. So you're adding 8/3, and you get negative 2/3. Now, I mentioned this to some of you up front, but isn't this supposed to be an area under a curve?
Yeah.
A negative area?
Yeah.
Yeah, take a look at what the graph looks like. What was the equation?
It was x squared minus 3
X squared minus 3.
in interval 1 to 2.
Let me change the window a bit. So we're supposed to find the area from 1 to 2, but look at where that is.
Every day.
It's underneath. Oh, that's all that means. A negative area is an area underneath the x-axis. You guys following? All right. Maybe a bit trickier with the square root. Yep. Change it to that, you guys. Right, Dave? Right? That's exactly what you did, right?
No, I didn't do that at all, actually. I did 3x to the 1/2 dx.
Okay. Well, you can take. Remember, you can take the constants out.
Oh.
What's the antiderivative here? X to the 1/2.
Learned that on previous
X to the 3/2.
X to the 3/2
Over 3.
over 3/2, which is multiplied by
2/3.
2/3. So the 3's are gone.
And then it's just 2x 3/2. Just like that.
So it's 2x to the 3/2, and then we evaluate that from 1 to 4. So the antiderivative at 4. Now you can use a calculator, but you guys really shouldn't have to. If you plug in a 4 here, the bottom number of a rational exponent is a root. So if it's a 2 at the bottom, it's a square root. What's the square root of 4?
2.
So then it's 2 to the 3rd power.
8.
And then 8 times 2?
16.
Well, it turns out to be a 16. And then if you plug in a 1, square root of 1?
1.
1 to the 3rd power.
1.
1 times 2.
2.
So it turns out to be
16 minus 2.
16 minus 2, which is 14.
Yay.
Okay?
Only you. Wow.
No, we didn't get to learn trig.
Good trick.
I hate what we got
Let's do some trig. You guys don't need lunch.
Can we schedule a meet after school?